Hello everyone and welcome to this lecture. In this lecture we will see a very beautiful theorem that we called friendship theorem. Okay, it was given by Paul Arados, Rennie and Verasos in 1966. This theorem tells that in a group of n people, if every pair of people have exactly one common friend, then there exists a person who is friend with everyone. Okay. At first glance it looked like what is so special about this theorem, but try proving it, it's not at all obvious. Okay, and we will prove this theorem using the concept of strongly regular graphs. It's again a surprising fact how these two things are related. And remember, we have just seen what strongly graphs are, right? These are graphs where if you pick any two adjacent vertices, they have the fixed number of common neighbors. Similarly, if you pick any two non-adjacent vertices, then they have again a fixed number of common neighbors. Okay, so let me first write down the statement, okay, of friendship theorem, very beautiful theorem, and then we will start proving it. Okay, theorem, friendship theorem. Okay, friendship theorem. Very good. In a group of n people, in a group of n people, if every pair of people has exactly one common friend, then there exists a person who is friend with everyone. Very good. Okay, so I hope the statement is clear. Okay, and now let us move towards proving it. What I will do is I will try to make a graph. I will claim about a graph and then we will prove that such graph may not exist. Okay, so and then we will reach to some contradiction to, and this contradiction will help us proving this statement. By the way, this statement can be stated in terms of graph. If it is a finite graph on n vertices where every pair of vertices has exactly one common neighbor, then there exists a vertex who is basically neighbor of everyone. Okay, so let me try to make a graph. Okay, so in fact I would say that there is a claim about a graph. Okay, so suppose there is a graph on n vertices, assume that this n is greater or equal to 2, or rather than greater than 2, where n is greater than 2. Okay, with the following conditions, with the following properties, okay, the first property is we will try to make properties in tandem with the friendship theorem. The first property is every pair of vertices has exactly one common neighbor. And another thing is every vertex has degree less than n minus 1. if this properties are following in this graph, okay, we will prove that then G is, or then the graph is regular. In fact, if we can prove that this graph is regular, we can prove more, right? It has to be strongly regular. Why? Because of first property, right? Every pair of vertices has exactly one common neighbor. So exactly one. So the parameters will be what? And suppose the regularity is k, so nk11. Okay, very good. So let us start proving it, that in that case this graph has to be regular. Okay, so proof of this claim. Very good. So so what? Let us take two, in this graph G, two non-adjacent vertices. Suppose this is U, this is V, and V and U have no edge between them. Okay, so these are non-adjacent vertices. Suppose U and V are non-adjacent vertices. Okay, so now what? Now by the suppose the degree of suppose the degree of U is k, that means degree, I will denote by degree of U is equal to k. Okay, very good. Now let me put these vertices below so that I have a space to draw this graph. Okay, so these are two non-adjacent vertices, and suppose the degree of U is k. Okay, very good. So these are the vertices. Suppose here U, then this is V. Okay, now degree of U is k, that means there are k adjacent neighbor, right? So one is, suppose this is W1, so W1 is first one to W2, and so on up to here Wk. Okay, so suppose these are the neighbors of U. Okay, now due to first condition, U and V have one common neighbor, right? U and V have exactly one common neighbor, right? So suppose by default W2 is common neighbor. Okay, so let me write here. Next, suppose W2 is the common neighbor, because there is just one, the common neighbor of U and V. Okay, now next thing is, now U and W2 will also have one common neighbor due to first condition. Okay, so suppose by default this is W1. Okay, so now similarly, so now let me write it here. Suppose W1 is the common neighbor of U and W2, Okay, now next, if you see that there will be a common neighbor of V with W2, W3, W4 and so on, right? So now if you see that, what are the so there has to be exactly one common neighbor, right? Suppose Zi is the common neighbor of Wi and V. Okay, so suppose Zi is some vertex here, okay, which is common neighbor of some Wi and this. Okay, remember Zi cannot be equal to Wi, otherwise what will happen, there will be two common neighbors of U and V, then the first condition will be violated. There has to be exactly one common neighbor. So let me maybe I can make here more so that it is pictorially more, so that the W3 and so on. So basically, so there will be such graphs. These are so Z3, there will be Z2, right? So it will be like this, right? yeah, and similarly this part also, right? So these are the common neighbors. Okay, so similarly zk will be somewhere here. Okay, this will be the situation here. Okay, now in this setup, if you see that how many what is the degree of V by there? Now remember these Zi's, right? So Zi is actually, so let me write here carefully so that this is more clear. So Zi is a common neighbor. In fact, the common neighbor, I would say, is the common neighbor of Wi and V for I equal to greater or equal to 2. Okay, so so what will happen? I mean, what about the degree of V? What can you say about the degree of V? Remember, I mean, till now what we have done is we have formulated how many neighbors of V. How many neighbors of V? How many Zi's are there? These Zi's are nothing but k minus 1, right? Z2, Z3 and so on, because I is varying from 2 to k, right? So there has to be k minus 1 of Zi's, right? And these are neighbor of V, right? But there is Z2 also with W2 also, which is direct, which is adjacent to V. So degree of V is at least k. So this implies degree of V is always greater or equal to k, right? But so that implies that degree of V is greater or equal to degree of U, right? But U and V were non-adjacent vertices, and we have started with V, right? We started with U. Same thing I can do from V's perspective. So by symmetry, I can claim that by symmetry, degree of U equal to, basically let me write more. So degree of V is less or equal to degree of U. Okay, and this further implies that degree of U equal to degree of V equal to k. Okay, so this, now what we have done, we have proven till now is any two non-adjacent vertices have the same degree. Okay, now what we have to prove? We have to prove that the graph G is indeed T regular or K regular here, right? How can we prove it? We have just proved that two non-adjacent vertices have the same degree. Okay. Now, if you focus on vertices other than W2, whatever the vertices other than W2, they will be either non-adjacent to V or non-adjacent to U, or both, right? Because there has to be exactly one common neighbor between U and V, which is W2. Other vertex cannot be common neighbor of U and V. So there has to be, for every vertex, either U is not adjacent or V is non-adjacent. Okay. So every vertex, next, every vertex other than, oh sorry about my writing, vertex other than W2 is either, again extremely sorry, either non-adjacent to U or V or both. Okay, so in that way all these vertices vertices will also have degree equal to k, have degree k. Very good. So till now we have proven that every vertex other than W2 have degree k. But what about W2? What about W2? How can we prove that W2 also have the degree k? Then we can prove that, then I mean this will imply that graph is regular, right? But how can we prove that W2 will also have degree k? The second condition will help us. Okay. The second condition tells that degree of every vertex is lesser than n minus 1. That means there exists a vertex which is not neighbor of W2, meaning that there exists a vertex which is non-adjacent to W2, hence W2 will also have a degree k. Due to 2, there exists a vertex non-adjacent to W2, hence W2 will also have degree equal to k. This implies finally all the vertices have the degree k. So this implies G is the graph is regular, in fact strongly regular, in fact strongly regular. Very good. And what are the parameters of that in strongly regular graph? Very simple one. These are nothing but there are n vertices, degree is k, 1 1. These are the number of common neighbors. Okay, very simple. Now remember, in the last lecture or maybe last lecture, I gave you one DIY exercise to find the eigenvalues and its multiplicities, right, of this graph, right? That was on purpose. The purpose is here now. Okay. So we know that there are three distinct eigenvalues. So one is by default k, other are suppose lambda plus and lambda minus. Okay. Suppose these are the eigenvalues, and there are corresponding repetitions of these eigenvalues that we call multiplicity. Suppose this is m plus and this is m minus. So these guys are always integers, right? M plus is just repetition, m minus again repetition, right? So these are this number. If you solve what m plus and m minus are, or from the DIY, you will see that this is, if you have not done this exercise, please do it first. You will see that m minus m plus is nothing but k divided by k minus 1. Okay, very simple fact. But this has to be integer. This is an integer. That means what? This has to be integer. That means this implies that k minus 1 square must divide it. This implies that k minus 1 square must divide k. Okay, and this implies that k is either 0 or 2. This implies that k is either 0 or 2, right? Very good. So now what will happen? So now let us take condition. Now graph is on what? So n is, we have given that n is greater equal to 2. Now k equal to 0 or 2. Okay. Now let us see the cases. Okay. By the way, when k equal to 0, when the regularity is, I mean every vertex degree 0, right? This is very, this is not possible due to those two conditions, right? Every vertex has, every two vertex has exactly one common friend, and then every degree is less than n minus 1. So this is false for k equal to 2. So only possibility is, so k equal to 0, I mean nothing is there, right? Now k equal to 2. Let us see k equal to 2. In that case, every vertex has degree 2. Every vertex has degree 2, right? Now let us see the case when k equal to 2 and n equal to greater or equal to 3. Let us see 3. In that case, graph will be this, right? But if you see that the first condition, in fact, so first condition is true for this graph, but what about the second condition? Second condition says that the degree of every vertex should be less than n minus 1, right? Here the degree is what? 2, which is not less than n minus 1 here, right? Very good. So this is also failed. Now let us take the third case when k equal to 2 but n is greater than 3. In that case, in this case, what will happen? What will happen? So let us take this case, right? First one, I mean let us take simple when n equal to 4. If you see that the first condition is not holding, right? First condition fail. Okay, so basically for any n greater or equal to 3, so the first condition first is not true. Not true here. The second was not true. Okay, very good. Okay, that means what? That means what? Such graph does not exist. This means that this implies that these cases imply that G or the graph, such graph, the graph does not exist. Does not exist with those with properties 1 and 2. Properties both 1 and 2. Okay, that means what? If the first condition, that implies that, now the proof is in our hand now. That means what? If the first condition has to be true, where every pair of vertices has exactly one common neighbor, the statement of Friend's theorem, the second one must be false, right? Second one must be false. That means what? The second statement was what? Every vertex has degree less than n minus 1. This has to be false. That means there exists a person who has degree, or there exists a vertex which has degree n minus 1. Okay, so that implies that if first is true, second must be false. Must be false. Okay, which implies that there will be a person, there exists a person, there exists a vertex, rather a vertex having degree n minus 1. That means what? There exists a person who is friend with everyone. Okay, so I hope you understood the proof. Very simple proof. We have tried to construct a regular graph with those two conditions. In fact, it was a strongly regular graph. Then we proved that this graph does not exist with those two properties, right? That means what? If first properties has to be true, the second one has to be false. That means there exists a person who is friend with everybody else, or other word in graph theoretical term, there exists a vertex which has degree n minus 1. Okay, so with this I am stopping this lecture. Thank you very much and see you in the next lecture. Yeah.